In this lecture, we're going to discuss the idea of function composition. So this is roughly the idea of doing one function followed by another function. And so in particular, if we're given two functions, so given functions, say f from general some set A to some set B, and G, and the idea is I want to do F followed by G, which means G had better start where F left off. So, see, this has to match here. The codomain of F should match the domain of G, so it has to match. Given functions F and G, we can define the composition of F and G. Composition. And here's, so I want to do F followed by G. You actually write it this way. G and then a circle, open circle, F. And it'll be clear in just a bit why we write it in this order. But yes, what we're really doing, this actually means do F, then G. So this composition is defined by the following formula. So, yeah, G of F of some element A, let's say, in A, is going to be, well, you do F of A, then you do G of whatever this says. So it's going to be G of F of A. And maybe this is the reason for this notation, right? Because this means I do F first, then I do G, right? I do G of F of A. So we just write it in the same order here when we use this circle notation, okay? So we're doing F first and then G. Okay, so that is the composition of functions. Let me draw a pictorial example. So let's say we have A, and then we have another set over here. Maybe it's a little bigger. And maybe we have another set. Maybe this looks like that. And let's go ahead and just draw some dots. So we have a few dots there, a few dots over here, and we'll draw a function. Let's make that dot go down to here. Say this one also goes to there. Say this one goes to there. And then, so this is my F here. It's a series of arrows. And then we have a few dots here. And now we have another function G. So I'm going to send everything in B somewhere, right? Otherwise, it's not a function defined on all of B. It's not a function on B. So let's make these first ones go here maybe. And then maybe we'll make that one go to that dot, and we'll make that one go to that dot. Right? And there needs to be an arrow coming out of every dot. That's what we demand as a function. And so this one is G. And so here's what F composed with G is. It's sort of this function where, yeah, it's defined on all of A. Must be defined on all of A. But then it goes here in this example, and then this is mapped to here, that's mapped to here. So we end up mapping all the way to C. So it's this composite function. You start with these inputs, and you get outputs all the way over here by just doing F followed by G. And again, we denote this as this function, G circle F. F followed by G. Okay. Let's do an example of the formula. So example, let's say let F be the function. So we'll do F be a function, let's say from R to R, defined by let's do E to the X. So it's E, and then G will be, let's say, again, a function from R. Let's do this actually. R without minus 1 to R, defined by G of X is x over x plus 1. Perfectly good function defined on this, right? That's my domain. This is not defined on -1, so I'm making sure to take it out of the domain. Okay, then so let's do 2 problems actually. So first of all, find where this composite function g circle f. So you do f then g. Let's find where it sends the number 0, which is a perfectly good number in the domain of f. All right. So let's go ahead and do that. That is, by definition, it is g of f of 0. And f of 0, that's e to the 0 by its formula, which is 1. So I've got g of 1. And now I need to figure out what g of 1 is. So that's going to be 1 over 1 plus 1, which is 1/2. Okay. Let's see if we can do even better. Can we just find a formula for g circle f? So find a formula. Find a formula for this composite function. Okay. Well, how do we do that? We have a formula for f. We have a formula for g. This is the function where we're gonna. This is our input. It's just we're plugging in for x here. Then we get this is our output. We are now going to take this output and plug it in for here for our input of g. So in other words, this is going to be g composed with f of some x. Sometimes you write with additional parentheses here just to emphasize not just f of x, it's this whole function. This is my name of my new function. Okay. Well, it's going to be g composed with f of x, but f of x is e to the x. So it's g of e to the x. But then what is g of e to the x? This is my input of g. It's the output of f, but it has become my input of g. So I plug that in for wherever I see an x here. So there's my formula for g composed with f is this function. Okay, so that's function composition. Let's look at some properties of function composition. So some properties. This will give us some practice writing some proofs as well. So again, let's keep our same setup. So let f from a to b and g from b to c be functions. So it makes sense to compose them. Well, it makes sense to compose them in the exact order we did, right? The output, the codomain of f needs to match the domain of g. So we can do f followed by g. First property is going to be that if f and g are both surjective, then, well, the natural question would be, is the composition surjective? And it turns out it is. G composed f is surjective. Okay, let's prove it. So how do we prove this? I'm assuming this, right? I'm assuming that f and g are both surjective. We're trying to prove an implication. I want to show this. I want to show g composed with f is surjective. So g composed with f, that's a function. Let's just remind ourselves up here. So g composed with f is a function from where to where? It's from a to c, right? So how do I show it's surjective? I take an arbitrary element over here, right, in my codomain, and I want to show that came from something here. I want to produce something here that maps to it. So I'm going to take an arbitrary element in my codomain. So let's let c be in my codomain c, and then I want to show there's an element here. Well, how do I know that? I mean, I don't from first principles, but let's use what we're assuming here, right? So I know that G is surjective. What does that mean? It means for my element here, I can find something in B at least, right? So let's write that. So since G is surjective, there exists a B and B, right? Such that G of B is C. Okay, so we use the fact that G is surjective. Let's use the full power of this assumption. We know that F is surjective, right? And we have an element over here in B, that little b. So since F is surjective, we know that that element gets hit by something, right? So since F is surjective, we know that there exists an A over here such that F of A is B equals B, okay? But this essentially proves it. Why does that prove it? Well, look at my element C, it's G of B, but B is F of A. So then let's just write that out. So C, this element C, can I find something in A such that G of F of that element is C? Yes, I've basically already done it. Let's just put all the pieces together. So C is G of B, but B is F of A, right? So I'm replacing that with that. And there we go. There's my element of A. Let's just write it in this form just to show that, yes, we have an element of A that we found. It's that one. That when you push it forward with this function, you get C. So that proves. So yeah, that's it. So yeah, G composed with F is surjective because C was arbitrary. Okay. Great. And this is also true if you replace surjective with injective. So should we do that one too? So if F and G are both injective, then this would be great practice for you to try also. You can pause the video and see if you can prove it yourself. And you can compare with what I'm going to do. And this is injective, right? Okay. So what's the proof? How do we prove that a function is injective? Well, here's what we do. We take, remember, injective means if I take, if I have two elements in here such that they're equal when you push over here, right? Such that they map to the same element, they had to be the same element to start with. Okay, so that's what I'm going to do. I'm going to start with two arbitrary elements in A. So I'm going to let A1 and A2 be in A. So this is I'm using the definition of injective here. I'm going to let these be in A such that I'm assuming that they map to the same thing over here. And then I want to actually prove that they were the same thing to start with. But I'm assuming this, right? I'm assuming that G composed with F of A1 equals G composed with F of A2. Okay? So the definition of injective, just to remind you, is if I have two things in A, then this being equal implies that A1 equals A2. So we want to show that A1 is going to equal A2. That'll be our last line here. Okay. Okay, well, what do we know? So we know that F and G are both injective. Let's first rewrite this. So i.e. G of F of A1, right, by definition of the composition, equals G of F of A2, right? But G is injective. G is injective. So see, I have G of something equaling G of something else. What does that mean? If G is injective, it means those two things are equal. Right? G is injective. So I have two things mapping to the same thing under G. Those had to be equal. right? G is injective. So that shows that f of A1 equals f of A2. But now f is injective. Since f is injective, f is also injective. A1 equals A2. We're done. Right? F is injective, and so f of A1 equals f of A2 implies A1 equals A2 by definition of injective. Okay. So that completes that proof. And putting these both together, so this is, I don't even want to know if I want to call it something separate. If f and g are both bijective, what can we conclude? Well, remember, bijective means injective and surjective. So this means f is injective and g is injective, f is surjective and g is surjective. Put these both together, we get that g circle f is injective and surjective, therefore it's bijective. We don't even need to write anything else. This is just a corollary of these two. Corollary means something that follows pretty much immediately from something we already proved. Okay, so here is a natural question we can ask. We have some if statements that we proved here, some implications. What about their converses, right? So what about the converses? Are the converses true? In other words, so if I know that the composition is surjective, does that mean that both my functions involved in the composition had to be surjective? And well, here's something we can definitely say. So let's think about the surjective case. So note, if my second function in the line, g, if g is not surjective, what do you think we can say about f composed with g? Well, g isn't surjective. If g doesn't hit everything, certainly f composed with g is not going to hit everything. And the reason is the outputs of f are going to be a subset of the inputs of g, and if all of those inputs of g don't lead to every element of the codomain, then yeah, certainly the composition is not going to. And so if g is not surjective, then this cannot be surjective. F composed with g, f then g is not surjective. And counterpositive of that would be, I suppose, if g composed with f is surjective, so it's counterpositive, which is the same statement, it's this equivalent statement. So if g composed with f is surjective, then g is surjective, right? I'm just writing down the counterpositive. Okay, well that's part of the converse, right? The converse of this would be if this is surjective, then both of them are surjective. Turns out that's not true. So it turns out that g does have to be surjective, but f need not be surjective. F need not be surjective. Okay. Let's see if we can come up with an example like that. So if f is going to be over here, and g is going to be here, here are my sets A, B, and C, A, B, and C, and we need g to be surjective, but f is not surjective, so f has to miss out on something here. We'll make only one element over there. Let's do it like this. So there might be a simpler example even, but we'll map both of these to here. So see, I'm rigging it so that f is not surjective. I do want g to be surjective, so we've got to map everything there. Yeah, I don't want to put another element in here. But notice, yes, f is doing f then g. Is that surjective? Well, yes, right? Because I hit everything in C. There's only one thing in C. But notice that f is not surjective here. Right? G is, but F is not, yet their composition is still surjective. So we don't get a full converse of this statement. And it turns out you can prove a similar partial converse of this second one. Okay, that's what it turns out. If G composed with F is injective, it's kind of the opposite of here. It turns out that F has to be injective, but G might not be injective. And you should try to come up with an example of that. Okay, so next thing I'd like to talk about is, this will be the last thing I'll talk about today, but this is a concept of, just because it's such an interesting concept, it's the idea of iterating a function. Iterating a function. Okay. And so given a function, given f from a space to itself, so x to x, has to be the same space, but if it is, well, we can compose the function with itself, right? So we can repeatedly compose f with itself. This leads to all kinds of interesting phenomena in math. So we can compose f with itself. So we can do f, we can do f composed with f, we can do f composed with f composed with f, etc. This is like the first iterate, second iterate, third iterate, etc. And this is something we might often like to do. We saw an example of this in the very first lecture, if I remember. It was the Collat's conjecture. In the Collat's conjecture, we defined f to be, so we define it as a function of natural numbers, and where f of n is, well, there are two possibilities. Remember, there was so if n is odd, then you multiply by 3 and then add 1, and if n is even, you divide by 2. So it's this one if n is odd, and this one if n is even. And in the Collat's conjecture, what we did was we start with a number, and then we kind of repeatedly apply this process. So for example, 7. Let me do one that actually where you can see the point sooner. So let's start with 3. And then we do 3n plus 1. That goes to 10. Then 10 is even, so it goes down to 5. And then 5 is odd, so we get 16, then 8. Then 4, then 2. 2 is still even, but 1 is odd, so we do 3 times 1 plus 1. That gets us back to 4, and we get trapped in this loop here. And so this Collat's problem, the Collat's conjecture is that no matter what you start with, you eventually get trapped in this loop. Okay, and essentially what we're doing here is we're iterating a function. So here's my 3, that's my first input. Then we do f of 3. Then we do f composed with f of 3. That's the 5. And we do f composed with f composed with f. You're repeatedly iterating this function. Okay, so a lot of problems have to do, interesting problems in math have to do with iterating a function. I'd like to give you one more example of this. This is another one of my favorite examples. So here's another example. So given a this is an unsolved problem as of the time of this video, by the way. The conjecture is that any starting number you end up in this loop, but that has not been proven yet. Here's another interesting function. So given a complex number c, we're going to define the following function. So we're going to define f, well, say f with a subscript of c, just to indicate this function is going to actually depend on that given number c that we're starting with, okay? And it's going to go from the complex numbers to the complex numbers. And it's going to be defined by this formula. So we're going to define it by f of some complex number. Let's call it z. Typically you use z for complex numbers rather than x. And it's going to be this formula, z squared plus that fixed number c that I'm starting with, okay? And here's what we want to do. Given a value so then we want to consider the iterates of this function. I want to consider the iterates. And what we want to do actually in this problem is we want to start with 0. So we're going to do fc of 0, and then we're going to do f, compose with 0, so etc. Right? So then this one, f of c of f of c of f of c of 0. So here's the function we're going to iterate. Okay, and we're going to do this for various values of c. Values of c. Okay. So here's an example. Let's say we take c to be the number 1. Okay. We take c to be the number 1. Then my function is, so f1, let's just write our formula. That's going to be this formula. Z squared plus 1. Okay, we're fixing that. We're locking this in now. And now we're going to consider these iterates. So we're always going to start with 0. And so here f1 of 0 is 0 squared plus 1 is 1. Right? Now let's look at the second iterate. So f of 1 of f1 of 0. Right? Well, it's going to be f of 1, which is 1 squared plus 1, which is 2. Okay? And then we'll consider the third iterate. So my output is becoming my input. You don't have to write this all out. But yeah, my output is my new input. And I get 2 squared plus 1. That's 5. You can keep repeating this. And you kind of get you can see what's going to happen. Like these numbers can get very large. Okay? Etc. Okay, let's take another value of c and see what happens. So c equals -1. So here I'm going to fix my new function. It is z squared plus -1. So z squared minus 1. Let's look at the iterates now. So we start with 0. We get 0 squared minus 1 is -1. Let's feed in the number -1 now. We got -1 squared minus 1. That's 1 minus 1 is 0. And then we have 0 that we're feeding in. And but wait a second, we already did that, right? So these are gonna loop back actually. I'm just gonna go between 0 and -1. Okay, interesting. By the way, did I mention this is a complex function? So we're allowed to plug in complex numbers. Let's do that. So let's plug in I, and then maybe this will be the last one I'll do. I'll show you what this problem's all about. We've got this function now, z squared plus I. That's my function I'm going to iterate. And so we plug in 0, we get 0 squared plus I, which is I. Remember, I is a number that has the property I squared is -1. We might need to use that in a second. Let's feed in I now. So f, just be consistent with where I'm putting this. So f of I is I squared plus I. I squared is -1 though, so this is -1 plus I. Okay. There's my new input. -1 plus I. And so I'm going to get -1 plus I squared plus another I. This one I might need to think about. So we can expand this binomial out. So I'm going to get 1 squared minus I minus another I minus 2I. And then I squared is a -1. So I'm going to get a -1 plus an I. So what does this work out to be? The ones cancel. I think I get a minus I. And you can continue this. All right, so continue iterating. Okay. And here's the big question. And this question, so this function is very simple looking, right? Z squared plus C. This is a big question. Or this is one of the questions we can ask. It turns out to be an extremely interesting question. So the question is, for what values of C? For what values of C do the iterates of fc of 0 remain bounded? Okay. Well, certainly this is bounded, right? I'm just staying between 0 and 1. This is unbounded. They get large, right? They get arbitrarily large. So a 1 is not a value of c. -1 is a valid value of c. It turns out I believe, is a valid value. In fact, I think if we go one more step, this just gets in the loop. And there are many other values that stay bounded, but there are also a lot of values of c that are unbounded. And if you plot all these values, this is actually what you get. You get this picture. You might have seen this picture before. So it's called the Mandelbrot set. And it turns out that this black area here, these are all the values of c plotted on the complex plane. Here's my real axis going this way, my imaginary axis going up this way. These are all the values of c such that these iterates remain bounded. Okay, I think 0 is somewhere around here. 1 is actually off here in this blue region. So everything out here, if you start with those values of c and you do this, it's going to get unbounded. Okay, and you might be wondering, okay, what about all these colors? Well, the colors aren't that important. So the values of c that remain bounded are just given by this black color in here. You see the structure is incredibly complicated, so you can very easily get values of c that are remain bounded and very close to ones that are unbounded in a very unpredictable way. The colors represent how quickly the ones that become unbounded actually become unbounded. So this one, it happens very quickly, right? These seem to get very large very fast. And so actually I think the point 1, the number 1 is somewhere out here. So it's well in this dark blue region. But you can see these yellows and even reds as you get closer here. And those are values of c. So the iterates, yes, they do eventually become unbounded, but it takes a really long time. It might take hundreds of iterations before they start to really become very large. So yeah, this just goes to show you that you can start with a very simple function and ask a function that doesn't seem too complicated, and you can just get a structure that's extremely complicated and beautiful, I might add. So it's a very beautiful set of numbers. It's called a Mandelbrot set. And you can even see when if you kind of look in here, you see smaller versions of the large set itself. So it has a fractal-like structure. You can even see things like there. So that's just an example of one of my favorite examples of iterating a function. Okay, I should leave it at that now.